Welcome to the first lesson, states of matter. So today we're going to learn what are the three states of matter, how the particles are arranged, so be able to draw particle diagrams, and how particles can convert from one state to another. So in the first instance, the three states of matter are solid, liquid, and gas. In a solid, the particles must be always touching and in a regular pattern. A solid has a definite shape and volume. On the other hand, in a liquid, while the particles still have to touch each other, they must still all be touching. They no longer have a regular pattern. Now, a liquid will have a definite volume. So if you pour one glass of 250 ml into a glass of 500 ml, then the volume will not change. However, if the shape of the container is different, the liquid will fill that shape. So they can change shape, not volume. Whereas solids, they cannot change shape. Now, a gas, the particles must not touch and they must be far apart and randomly arranged. So in here, gases are compressible, which means that if you apply pressure, you can bring the particles closer together into a smaller volume. That's unlike the other two. So gases will take the shape of the container and can also be compressed and change volume. Now, in terms of strengths of attractions, a solid has the strongest attractions between the particles, holding them together. The particles have the least energy and they just vibrate. Unless you're at absolute zero, particles are always vibrating. In a liquid, the particles are less strongly attracted to each other than a solid. So they can move and slide over each other, but they're still touching. The energy of the particles is higher. In the last case, the gases, the force of attraction between them is the weakest, but the particles themselves have the highest energy because they're moving around freely until they collide with each other. So those are the three states of matter. If we look at how to draw them in an actual box, then actually this is not perfect. It needs to start at the bottom of the box. So if you have a square, you must start here. 1, 2, 3, 4. So you must touch. 5, 6. Then you must continue touching each other and having a regular pattern. So this is not wrong, it's just it's not touching the bottom, so they will mark it incorrectly. So just make sure you do it like this. You don't have to fill the whole box. You can do 2 or 3 rows, that's fine. Liquid, the same thing. Make sure you start at the bottom, otherwise this diagram is correct. So it should just not form a pattern, but they need to always touch. So for example, here, these are not touching. The examiner can be strict and mark that wrong. So make sure they all touch. In a gas, they should be far apart and irregular. So these are far apart and irregular. So don't think of a liquid as an intermediate between a solid and a gas. Okay? Don't think that the particles are going to be slightly apart in a liquid. They're not. They're still touching. So if you have your diagram, you have your liquid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. Just don't go drawing a weird snake either. That's a liquid. Now, converting between the states of matter, we have here. So we have solid, liquid, gas. To go from a solid to a liquid, it's like ice melting, so it's melting. To go from a liquid to a gas, you have 2 choices, evaporation or boiling. Each one we'll discuss in turn. Now, to go backwards from a gas to a liquid is condensation, and is what you see on your mirror after you've taken, say, a hot shower and the mirror is cold. As the gas cools down, it condenses. And lastly, we've got liquid to solid, which is freezing. So that's how you form ice cubes. Now, sublimation can both mean a solid going to a gas directly with no melting, or a gas going back to a solid. Some people, or in an American way, you would say desublimation for gas to solid, and sublimation for the solid to gas. So sublimation occurs because the melting point and the boiling point are equal, so there is no liquid state. Now, evaporation can occur at any temperature, and it can occur when some particles have enough energy to escape and break the force of attraction between them. So, for example, you would say that a puddle, my face is in the way. You would say a puddle evaporates because a puddle doesn't boil at 100 degrees. A puddle can evaporate even at 15 or 25 degrees. Obviously, it won't work at negative temperatures. So evaporation happens at any temperature, whereas boiling is a fixed temperature. So, for example, water has to be at 100 degrees Celsius and is defined as when all the particles have enough energy to escape and break the force of attraction between them. Whereas evaporation is when only the more energetic particles can escape, which are going to be at the top of the liquid. Lastly, if we look at the energy changes associated with each process, which is a bit of a higher level thing, let's have a look at this. So going from a solid to a liquid, you're melting. So you need to take energy in to break the bonds apart between the particles and loosen them, not fully break them. Then from a liquid to a gas, when you boil, again, heat is taken in. So both of these are called endothermic processes. Energy is taken in to break the force of attraction completely between the particles so they can be far apart in the gas. On the other hand, if you're going from a liquid to a solid, so you're freezing, this is a bit more difficult to get your head around. The particles are starting from being loosely apart to then be in a particular pattern and even closer together. Both times still touching, but even closer together. So that will actually release a slight bit of energy out. It's called exothermic. It's a type of bond-forming process that you'll cover later on. And when you form bonds, think of a collision between two cars. They release energy. So energy will be given out as the particles bond together. It's perhaps easier to think of it as gas to liquid. The particles are far apart, they now need to come and touch each other. That releases energy. And because of the conservation of energy, whatever energy you need to boil the liquid to a gas where energy was taken in will be equal to the energy released when the gas to liquid phase forms. So endothermic, heat energy taken in, exothermic, heat energy given out. And perhaps the last thing to emphasize here, in this little summary, is that particles in a solid are always vibrating. Unless they're at absolute zero, they will vibrate. They don't start to vibrate when the solid is heated. They're already vibrating. So if someone says what happens when a liquid melts, a solid melts, the particles will vibrate more. Don't say they start vibrating. They're always vibrating. So they vibrate more to overcome the attractive forces. If you go from liquid to a gas, the particles move so fast, they have enough energy to break the attractive forces completely and escape. And for the reverse process, if you cool a gas, the particles move slower until the attractive force, when they get close together, is strong enough to hold them. And when you go from a liquid to a solid, the particles move even slower until the attractive force holds them in fixed positions so they can just simply vibrate. And that covers these spec points. Just to show you sublimation, physical process when a solid directly changes to a gas or when a gas cools to reform the solid. So your teacher may demonstrate this using ammonium chloride vapors because ammonium chloride breaks into ammonia and hydrogen chloride, and then it reforms at the top and they cool down again. You will see this in the reversible reactions topic and when we do diffusion. More likely, they might show you the sublimation of iodine from a dark gray solid to a purple vapor. That's the end of the first lesson on states of matter.